Welcome back to part 2, where I define the model carefully and discuss the main theorems that we are going to prove. Okay, so let me start from some definitions. These are standard, but I want to fix notations. So we consider the L by L square lattice, which we denote by lambda L, and where L is, of course, a positive integer. Okay, so lambda L is defined like this. So the element of lambda L is denoted. It's called a site, and we represent site like this. And it can be represented in this way, where u1 and u2 are the x coordinate and y coordinate. They take these values. So this is the example, lambda 3. This is 1, 1, 3, 2. And so this is 3 by 3 lattice. And we also define, for convenience, we also define a larger lattice, lambda bar L, where we added 0 and L plus 1 here. So this whole thing is lambda 3 bar. It's actually 5 by 5 square lattice. Okay. And then if you take away lambda L from lambda bar, then this remaining here, this orange region, is called a boundary. Okay. This is convenient for defining boundary conditions. Okay, we discussed set of bonds. A bond is, well, a bond is a pair of two sides, and we don't care about the ordering. So they are just pairs, but in picture we represent a bond by a segment, this kind of line connecting two sides. Okay, so this is the most basic set of bonds. It consists of pair of UV, where the distance between U and V is 1, and UV belongs to lambda L. So in case of lambda 3, these green segments denote the element of BL. We also define B bar L for the larger lattice. Again, they belong to lambda bar, larger one, and the distance between U and V is 1. But we also require that it doesn't happen that both of U and V belong to the boundary. Okay, so without this condition, we have to consider all these things. But we don't need these bonds. So this is, well, I think the picture will enough. This is enough. So this is the definition of B bar. And this is for periodic boundary conditions. So we start from BL and add these bonds, but it's much easier to look at this picture. So we want to implement periodic boundary condition. That means we want to add here a bond that connects here and here, for example. So these are actually two pieces of a single bond. So this guy is connected to this guy to this guy. I think this is clear, but if you look at this formula carefully, we are doing this. Okay, so these are set of bonds. Now we go to Hamiltonian and under three different boundary conditions. First of all, by a spin configuration, we denote a collection of these spin variables, which takes value plus or minus 1. Okay, this is the Ising model. For each site u, we have spin variable sigma u that takes value either plus or minus. Okay, and so this is a collection. So since each spin can take either plus or minus, they take two values. There are essentially 2 to the L to the squared distinct configuration, spin configuration. And I know, so this is my S. So I denote by SL the set of all possible spin configurations. So there are so many elements here. Okay, then the Hamiltonian depends on the system size L, the external magnetic field H, which takes real value, and the boundary condition, which is either free, periodic, or plus. Okay, and it's a function of spin configuration. Okay, and here are definitions. And so first of all, this is the most basic one, Hamiltonian with the free boundary condition. And in this case, this is the interaction part. You have minus sign and sum over all basic bonds. And here is an interaction on the bond, sigma u times sigma v. And we say that this is ferromagnetic interaction because if you want to lower the energy, then you want this product to be 1. This means that they are both plus 1 or both minus 1. So in order to lower the energy, these two spins should align in the same direction. So this means that we have ferromagnetic interaction. This is the magnetic field term. And then in this case, if magnetic field H is positive, then we want this sigma to be positive to lower the energy. And if H is negative, then we want this sigma to be negative. Okay. And this is the free boundary condition Hamiltonian. And we also define Hamiltonian for the periodic boundary condition and the plus boundary condition. And actually, these magnetic field parts are exactly the same. Okay. And this is a periodic boundary condition. Well, it's just clear. So we replace this BL by BL periodic. Okay. So we replace this by this to include all these interaction. And this is very convenient. It makes the problem translation invariant. And this is a plus boundary condition. Now, in this case, we have sum over all bonds that belongs to B bar. This, oh, no, it's here. These blue lines represent bonds in B bar. And again, we have the same interaction. But we have to be careful. In this case, this sum includes U of V, which is out of this sum, lattice lambda L. And this spin configuration is only for spins on lambda L. And in this formula, if you encounter sigma V for V, which does not belong to this center lambda L, and in other words, which belongs to the boundary, and then we just set sigma V to be 1. Okay. So this is called the plus boundary condition. We have lambda L here, and outside we have these fixed plus spins. Okay. So these are the three basic boundary conditions we consider, and actually we need all of them. And of course, you can consider many, many other boundary conditions, but anyway, these are necessary and sufficient for us. Okay, so this is just a quick review of statistical mechanics, the canonical formalism. So the canonical distribution at inverse temperature beta, which is 1 over kBt, is defined as follows. So first of all, the partition function is simply the sum over all spin configuration and of e to the minus beta h. Okay. Well, so this depends on system size L, parameters beta h, and also the boundary condition. Okay. And then the free energy density is defined like this. So if you take log and just divide it by beta and might put minus, then you get free energy. And then we want to have free energy density, so we have L squared here. Okay. And then for any function of spin configurations, its expectation value with this boundary condition, system size L at these parameters is defined like this. Okay. This is normalization, and you sum overall spin configuration. This is a unknown function. This is a function that you want to take average, and this is the Boltzmann factor. Okay, so again, this is very standard. As an exercise or warm-up, I want to review the expression of the magnetization density for finite system. Actually, we do not use this as our definition, but this will be anyway useful. So first of all, let us differentiate the partition function by h. So if you recall, the definition of partition function is this. So if you differentiate this by h, then you just differentiate here. So this minus beta comes down, and you have this. But now if you look at the definition of the Hamiltonian, it's here. H appears here, and it's exactly the same for all the three boundary conditions. Okay. So if you differentiate h with Hamiltonian with respect to h, then you get this thing, right? So it's this. Okay. Derivative is given by this. So if you consider this thing, the derivative of log of z, then you get this. So you just plug this in here. So you have two minus signs, so you don't have any minus sign, and you get this. But now it's clear that this is the definition of the expectation value. So now this is log z. So if you put minus sign and divide this by L squared times beta, you get the free energy density. So the derivative of the free energy density becomes like this. So here, what you have here is the expectation value of the magnetization density. This thing here is the total magnetization. Okay, the total spin, which is can be interpreted as the total magnetization, and you divide it by the number of spins, okay, number of lattice sites. All right, so well, this was a warm-up exercise, and now I like to tell you what are the main theorems. So I start from theorem 3. I don't have any theorem 1 or 2. I call this theorem 3 because this is proved in part 3. Okay. Now, this very important theorem says that for any inverse temperature beta and for any magnetic field H, this limit, okay, exists. So that we fix beta H and let L go to infinity, and then this limit exists. And also it is independent of boundary condition. Okay, of course this quantity depends on the choice of boundary condition, but if you let L go to infinity, then there's no dependency, and you get this F beta H. And this F beta H can be proved to be concave in H and satisfies this symmetry. Okay, so this is a very good news, especially this independence to the boundary condition is very good news. This tells you that we have free energy that represents idealized thermodynamic property of the system. Okay, and so this L going to infinity limit is usually called the thermodynamic limit or the infinite volume limit. And you recall that this is the same as what we had in part 1. Okay, in part 1 we claim that we get this from thermodynamics and symmetry of the system, and we precisely have the same statement as a theorem. Okay, and so we define magnetization density by using this universal free energy, which is independent of the boundary condition. And again, this is part 1. I'm sorry, this is part 1. So this is the same as the definition we gave in thermodynamic definition we gave in part 1. Okay, but of course this is when F is differentiable in H. Okay, and of course, as I said before, sometimes F is not differentiable. So when F is differentiable in H at H equals 0, then this means that it's an even function. So you automatically see that this magnetization density is vanishing. It's 0. But sometimes F is not differentiable, so we define this spontaneous magnetization. Again, this is the same as what I discussed in part 1. So this is the right derivative, which always exists because of the concavity, and so it's written like this. So we define spontaneous magnetization this way. And these are two very important essential theorems. First of all, theorem 4, which would be proved in part 4, says that there is a constant beta H, H means high temperature, and such that for any beta less than or equal less than beta H, this spontaneous magnetization is 0. So nothing weird happens. Okay, so this is differentiable at H equals 0. And then this is the opposite thing. Theorem 5 says that there is beta L, this means low temperature, and for any beta larger than beta L, this spontaneous magnetization is strictly positive. Okay, and we also see that this spontaneous magnetization approaches 1 as beta goes to infinity. So this is a 0 temperature limit. Okay, and so this establishes that this free energy density is non-differentiable in H at H equals 0. And there are two, so we see that, so this is a very rough phase diagram. So this is the beta axis. So what we have seen is that in this high temperature region, small beta region, ms is 0. And in this low temperature region, large beta region, we see that ms is non-zero. Okay, so there must be a phase transition in between them. And I stress that this beta H and beta L are not equal. So these are actually not optimal theorems. They may be improved. And what we expect, and actually this can be proved, it's much harder, but it can be proved that the system only has two phases, this high temperature phase, paramagnetic phase, and this low temperature phase, the ferromagnetic phase, separated by a single transition point. But anyway, these two theorems establishes that there must be a phase transition between beta H and beta L. Okay, So these are what we are going to prove. So okay, so we are going to prove this theorem 3 in part 3, theorem 4 in part 4, and theorem 5 in part 5. Okay, so this could be the end of part 2, but let me make some advanced remarks. The first remark is about the characterization of spontaneous magnetization. So here we defined spontaneous magnetization this way by using the right derivative. So you may call this a thermodynamic definition. And here is a different definition, which may be called a statistical mechanical definition, and you can prove that they are equivalent. But actually, this proof is not easy. But anyway, for the Ising model, you can prove it. Okay, so what is this definition? Well, anyway, you fix a boundary condition, and you take finite L, and you fix beta, and take some finite positive H. And you consider this expectation value of the magnetization density. Then you fix beta and H, and take the limit in which L goes to infinity. And after this infinite volume limit, you let H go to 0. Okay, and so this actually gives exactly the same thing as this right derivative for the Ising model. Okay, and this is just a characterization, but here is a very important remark. So suppose that our boundary condition is either free or periodic, and in this case, the Hamiltonian with zero magnetic field satisfies this symmetry, global spin flip symmetry. Minus sigma means the spin configuration in which all the spins are flipped. Okay, and when you don't have any magnetic field, and if you have free or periodic boundary condition, the Hamiltonian satisfies this. And by using this symmetry, you can easily prove that when magnetic field is 0 and L is finite, this expectation value of the magnetization density is always 0 for any beta. Okay, this means that since this thing for finite L is continuous in H, this means that this limit with finite L is equal to this, and it's 0. Then whatever you do, it's still 0. So you find that this limit is 0. And now recall that this is spontaneous magnetization, and in dimension d or higher, if beta is large enough, this is non-zero. Okay, so this is very interesting. Sometimes people say that in physics you're allowed to exchange the order of limits, but of course you cannot do it even in physics, especially in this case. So here you take the infinite volume limit first, and then let H go to 0. Then you may get non-zero value at low temperature. Okay, but if you first let H go to 0 and then take the infinite volume limit, you always get 0 for any beta. Okay. So of course there is something very subtle and delicate is going on, and that is called spontaneous symmetry breaking. Okay, so roughly speaking, what happens here is that when ms beta, this is non-zero, this means that this symmetry and its consequence is broken by this thing, which may be interpreted as an infinitesimally small magnetic field. Okay. So this is why people call this spontaneous breakdown of symmetry. Okay, you don't have any H anymore, but still the model breaks its symmetry. Okay, so this was the first remark, and the second remark is about more refined results for the d-dimensional Ising model in any dimension greater than equal to 2. So we discussed some early rigorous theorems, but of course there are many strong theorems proved for the Ising model, and these are just only part of them. Okay, so first of all, this is the consequence of something called the Li-Yan's theorem. It's a very old theorem, and we know that this derivative exists, and it's continuous in H if H is non-zero. Okay, this is worth knowing, and these are about phase transition. So in any dimension d greater than equal to 2, we know that there exists a unique transition point beta c, okay, and which depends only on d. And in dimension d equal 2, we know the exact value of beta c, but in other dimensions we don't know any exact values. But we are sure that we know that it has been proved, but that there is a unique beta c with these characters. Okay, first of all, this may be a definition of beta c, but we see that it is ms beta, the spontaneous magnetization is 0 when beta is less than or equal to beta c, and it's positive when beta is larger than beta c. Okay, and well, actually, this is a very difficult theorem, but some people can also prove that as beta approaches beta c from above, then this ms beta approaches 0 continuously. Okay, and here's something about low temperature region, high temperature region with smaller beta. And when beta is less than beta c, we can define something called susceptibility and prove that it is less than, it is finite. So what is this? Well, this is simply the derivative. So recall that in this high temperature region, M, the magnetization density is 0 when H equals 0. But you can so it's 0 when there's no magnetic field, but if you apply a small magnetic field, that you get some small magnetization. So this derivative tells you how easy to magnetize this system. Okay. And that's called susceptibility, and you can measure this by experimentally by applying a small magnetic field to your magnet. Okay, and so this is finite in this high temperature region, and you can also prove that as beta approaches beta c from below, that means from high temperature, this susceptibility diverges. This has been proved rigorously. Okay, so these are quite interesting. So at this point beta c, this MSB, spontaneous magnetization, vanishes continuously like this, and also chi beta diverges like this. And these are two typical examples of a bunch of phenomena called critical phenomena, set of phenomena called critical phenomena, that takes place at or near the critical point beta c. Now this is sometimes called the transition point, but sometimes called the critical point. Okay, and these critical phenomena are, of course, very interesting topic of study. But in this mini course, I don't have any time to talk about critical phenomena. Okay, so that's all for part 2.